Hi, my name is Kate, and this is Lab 4 for Physics 2211 called Oscillations. This lab is meant to show the motion of a spring traveling both vertically and horizontally, meaning the same mass with two different oscillation patterns. This may seem complicated, but it's actually pretty simple to explain using basic physics principles. To do so, we inputted a video of a mouse on a spring with the motion in the tracker and then formed a computational model based off the data. One of the main principles we are going to use is Newton's second law. This can be manipulated into the momentum principle, which can further be broken down to find the velocity update and position update formulas. These will be used to track the object's motion to form two separate position versus time graphs. We were told the mass starts motionless, hanging on the spring before it is pulled down or released. During this state, we can use the fact that a motionless object means it's in static equilibrium. This implies that F net equals 0, and we can set the sum of the forces equal to 0. This will help us find some missing constants later. There are three different energies present in this experiment. Kinetic energy describes the actual motion of the object, while the gravity potential and spring potential show what will happen to the object. All of these add together give us the total energy of the system. It is easiest to include everything in the system and nothing in the surroundings. This includes the spring, the mass, and the earth. When we do this, it means no external work is being done on the system. The mass of the object is 0.402 kilograms, which was said in the pre-lecture video. The object's initial position is negative 0.121. negative 0.3630 meters, and this was found using tracker. Like I previously said, the external work on the system is 0. Q, which represents the heat entering or leaving the system, is also 0 because it can be considered negligible for this scenario. This means that the sum of the changes in energy can be set to 0. This should be reflected in our graph later. To find the spring constant, also known as the spring stiffness, we can use the period of oscillation. The time period used above was found in the pre-lecture video, and it can be used because the same spring and mass were used for our experiment. The spring constant of a specific spring stays the same regardless of what type of experiment is occurring, because it is a property of the spring. To find the relaxed spring length, we use Newton's second law for an object at rest. Before we track the object in the video, we calibrate tracker to the specific video so that we can get accurate data. Tracker produces two graphs, one for position in the x direction and the other for position in the y direction. I put the data produced from this into a spreadsheet, which is later inputted into GlowScript to compare the computational data to the experimental. For the computational model, we first plug in the initial values and constants. These values are the object's mass, position, and velocity. The initial velocity is 0 because the object is released from rest. It is also true that at the object's peaks, the velocity is 0 because it is fully changing directions. Next, we specify the direction and magnitude of the stretch of the spring used for the spring force and spring potential energy. S is equal to L minus L net, or L initial, which is the L initial we previously found. We also plug in all of the energy equations. Here we define the initial energies so we can later use them to find the change in energies. The change in energy is found by subtracting the initial energy from the final energy. This is the graph that is produced from the computational model, and it represents how the different types of energies change throughout the time period. The orange line shows the change in total energy. As we can see, the line stays at 0 the whole time, which makes sense because work external is equal to 0. As we can also see, all of the energies typically line up or cross paths at the orange line. Here are the position versus time graphs. The computational model lines up with the experimental data fairly well. These graphs sort of look like cosine or sine graphs, which lines up with the idea that the object is oscillating. The term oscillating just means that an object moves back and forth at a regular speed, explaining why it has the same time period for each oscillation. The x graph looks more like a pendulum, while the y graph looks like a vertical spring, which is what we saw in the pre-lecture video. Potential error could come from the fact that we didn't account for external forces such as air resistance, even though it's safe to assume it is negligible in this scenario. Another factor that was considered negligible was the loss or gain of heat. The most probable source of error was from potential human error because the video wasn't great quality. Is the energy principle satisfied? Yes. No surroundings means the total energy is equal to 0, and this was shown in the graph. The kinetic energy started off with large peaks that slowly became smaller as the object slowed down. Potential gravity energy and potential spring energy were inversely related with roughly equal magnitude, which lines up with the idea that F net equals 0. We can find two different time periods by reading off the two position graphs. For x, we get the value 1.67 seconds. For y, we get the value 1.52 seconds. These values are different because the object is moving in both the x and y directions, creating two different behaviors with two different oscillation periods. In conclusion, we learned that complicated scenarios can actually be explained with simple physics principles. Using the energy principle and Newton's second law helps us understand the wonders of the world. Thank you.